Okay, so the next shape we're going to talk about in geometry is circles. There's going to be a ton of vocabulary here up front, so feel free to stop the video at any time and write in the definitions as I talk, and then start it back up, and I'll explain a little bit more about what we're looking at. Okay, circles, and there's going to be lots of angles and lots of segments that we're going to create and talk about. And so we got to find a way to keep all that straight. Okay, now, first things first is, what is a circle? And a circle is a set of points that are equidistant from a given point that we call a center. And the reason why a circle is curved is because if this center point was Q, and this point out here was P, and this point were M, if I were to draw a segment to represent the distance from Q to P, okay, and then draw a segment that represents the distance from Q to M, then obviously the segment QM is going to be a lot longer than the segment QP. In order to shorten that segment QM to where it's the same length as QP, we'd have to move M this way. And as a matter of fact, we have to move M so close that M would have to be right next to P, and even then it would have to come off of that line a little bit. So to maintain that distance, the points are going to have to sort of curve around and rotate around point Q. So the reason why a circle is curved is because it has to be, in order to keep a distance that's the same from this center point. Okay? Now, we just talked about the distance from the center to a point on the circle, and that is what we call the radius, and we've seen radius before. The radius is the distance from the center to a point on the circle. Now, it's also a physical thing. It's a physical segment, and the definition of this physical segment is a segment whose endpoints are the center of the circle and on the actual circle. Okay? So it's a segment, and it's also a measure, and we'll use it in either way. Now, since we're talking about a radius, two circles are going to be congruent if they have the same radius. Not the same center. They need to have different centers, because if they have the same center and the same radius, then they'd just be the same circle. But two circles are congruent if they have the same radius. Okay. Next up is the diameter. Okay. The diameter is the distance across the circle, but it specifically has to be the distance across the circle through the center. Okay, and just like a radius, the diameter can be thought of as an actual numerical measure, or a chord that passes through the center of the circle. Now, what's a chord? A chord is a segment whose endpoints are on the circle, but it doesn't necessarily have to go through the center. Okay, so the blue segment here is the diameter because the endpoints are on the circle, and it goes through the center. Now, since that's the case, hopefully you remember that the diameter is twice as long as the radius, and the radius is half as long as the diameter. And we can always talk more about why if you need to. But a chord, just any chord, so a diameter is a chord because the definition of a chord is a segment whose endpoints are on the circle. Now this yellow guy here is a chord because the endpoints are on the circle, but it doesn't go through the center, so it's not a diameter. So a chord doesn't have to be a diameter. And the last definition here for you is a secant. And a secant is basically a line that intersects the circle in 2 points. I said this is the last definition. It's not. There's one more. But a secant is a line that passes through the circle at 2 points. So everywhere you see a secant, there is a chord. And everywhere you see a chord, you could draw a secant because segments are just parts of a line. And then now the last definition is a tangent line. And a tangent line is this purple guy. And a tangent line is a line that touches the circle at exactly 1 point. Okay? Tangent lines, those of you guys heading to calculus in your future, that'll be a big part of what you talk about. All right? So, identify some of the parts in this diagram. which I do believe is a little bit different than the diagram in your notes. Okay, so let's stick to the way the points are labeled in your notes. Okay, I believe this guy is B, and this guy is A. The center is G. This is C. This is F. E. This is D. And then this guy up here is H. Okay? Now, go through, stop the video, see if you can't come up with some different examples of these parts, and I'll show you what I came up with. Okay, and so there we go. The center is at G. A secant line, line AB. Make sure that your line symbol is used here, not a segment symbol. Because if you use a segment symbol, it's going to be a chord. So make sure that you label it with a line symbol. Tangent line segment, you could use HD. Is actually the only one you could use. The diameter, CE. A radius, GF. You could use GE or GC. Right? Make sure, again, you're using the segment symbol. And then a chord. A chord, you could use CE, use the diameter if you want, or we could use the secant line AB to name a chord, segment AB. Okay? Now, while we're here, to name a circle, we use the center point. So this is circle G, but we just can't leave it at G like that because that's how we name points. So what we do is we also use a circle symbol in front, which is just a circle with a dot in the middle to represent a center. And so that's circle G. Okay? Now, there are some theorems for you. Okay, and again, you can write these in, and if you need to stop the video to do so, do that. Okay, but I'm going to go ahead and talk about these. The first theorem, 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. What does that mean? It basically means that if line M is going to be a tangent, it would have to be perpendicular to radius QP. Okay? And that's the statement that you're going to want to write in your notes. Okay? Line M is tangent to circle circle Q, if and only if it's perpendicular to QP. Now remember, perpendicular lines form right angles, and we could always finish off and make this make a triangle here and have a right triangle, which means everything that we know about right triangles come back to play. Right Pythagorean theorem, sine, cosine, tangent, special right triangles, and all that kind of stuff. All right, so just be aware of that. The next theorem, if two segments from the same exterior point are tangent to a circle, then they are congruent. Okay? This is kind of called the snow cone theorem, because when you draw these in, you kind of get a picture that looks like a snow cone. So when you see a diagram that looks like a snow cone, then the snow cone sides are going to be congruent here and here. Right? So if SR and ST are tangent segments, then SR and ST are going to be congruent to each other. And it doesn't matter if point S is closer to the circle or not. Okay? SR and ST are still going to be congruent here. All right? Now, I'll also back up real quick because you may see this at some point. But tangent lines, where they meet the circle, they meet them at a point of tangency. It's what that point is called. And we may not use it a ton here, but you may see it written someplace else. So that's the point of tangency, abbreviated as POT. Okay, so insert your giggle here. But a point of tangency, so we'll talk about radii and tangents meeting at a point of tangency. Okay? Now, how to use these examples? Well, from theorem 10.1, just very generically, if we have a circle and we draw in a radius, so we can draw in a radius here, and then there's this tangent segment here, then we can, like I said before, draw in another segment to help complete this right triangle. So if AB is tangent to circle C, and we draw in radius CB, they're going to be perpendicular to each other. So we get this right triangle, and to find x, we use the Pythagorean theorem, right? Leg squared plus leg squared equals hypotenuse squared, where the legs are x and 32. And the hypotenuse, this is what you got to be kind of careful with. This whole length is x plus 16, because this is the segment addition postulate that we're going to use. And so we have to add x and 16. So x squared plus 32 squared would have to be equal to x plus 16 squared. Okay? And so x squared, so we go to work this out, x squared plus, and this is 1,024, I believe. Okay? Equals, and when you square x plus 16, you should get x squared plus 32x plus 256. And if you need me to go through that, come see me. Now, good news is when we subtract x squared from both sides, these x squareds add to 0. So we're left with this equation here. Subtract 256, divide by 32, and x ends up being 24. Okay? Now, you can try your hand. Try your hand at number 2 here. A little bit more realistic or real life application. Still not the best application, but we'll take it. Swimming pool, you're standing 36 feet from a circular swimming pool. And the distance from you to a point of tangency on the pool is 48 feet, as shown. What's the radius of the pool? Maybe you need to know the radius. Well, this is going to set up a lot like number 1. So give it a shot, stop the video, work it out, and then start it back up and see if you got it right. And so hopefully you got R to be 14. Okay? Now a quick review on squaring this binomial if we need it. Just write them out, right? When you square something, you're multiplying it by itself. So write your 2 binomials being multiplied out, and then you FOIL it, right? First, outer, inner, last. Combine your like terms, and you should come up with R squared plus 72R plus 1296. Okay, a little bit of algebra review there, but useful. All right? All right. Now, your theorem 10.2, basically like I said before, the snow cone theorem. Snow cone theorem says the sides of your snow cone are going to be congruent. So if these are segments, then KJ and MJ are going to be congruent. So quite simply, you set these equal to each other and go solve for x. And so x is going to be 5 for number 1. Take a couple seconds, work out number 2, and I'll show you the answer. And you should come up with x equals 2. Okay, just set those 2 segments again equal to each other. Okay? All right. Section 10.2 talks about arc measures, and we're going to have a lot of vocabulary in here. Okay? Arc measures. First of all, we have to know what a central angle is. A central angle is an angle whose vertex is the center of a circle, right? Pretty simple. So down here, angle APB is a central angle because its vertex is at the center. Okay? Now, if the measure of a central angle, so if APB is less than 180, so it's less than a straight angle, then points A and B that are on this circle here are going to create what's called a minor arc. So points A, B, and all the points in between A and B are going to create a minor arc. So this is minor arc AB, and the notation that we use, and you kind of see it here, but it's written a little rough, is going to be AB with an arc above it, if I can't make it any better. Just like that. So we use the endpoints, and then we put an arc above that to know what arc we're talking about. Okay, and that's a minor arc. So the points in between A and B are a minor arc. Now, the points outside of A and B, or outside of angle APB on the circle, are called a major arc. So this guy is a minor arc, then that means this guy is a major arc. Okay? Since that arc is bigger than the one we were just talking about. Okay? Another quick thing, another quick definition for you here is if the endpoints of an arc are the endpoints of a diameter, then the arc is a semicircle. In other words, we're cutting the circle in half. So this guy right here, call it, I don't know, DE, is the diameter. So angle DPE would be a straight angle. And so it cuts the circle in half. So there's this guy and this guy that are semicircles. Okay? Now, notation. How do we name major arcs? Well, minor arcs, we use the endpoints and an arc symbol above it. But for a major arc, we can't do the same thing because we won't know, because we can't call this major arc arc AB because we won't know if we're talking about the minor arc or the major arc, which sets of points are we talking about. So what we do is we introduce a third point anywhere else on that circle, and we use that third point to help name our major arc. So we would name this major arc, and you see it over here too, but again it's written kind of rough, but AQB with an arc symbol above it. That's your major arc. Okay? Some more definition. The measure of a minor arc is defined to be the same as its central angle. Okay? So whoever, probably Euclid or somebody a long time ago decided, you know what, we already know what an angle is and how to measure an angle. So why don't we just say that the measure of the minor arc is the same? Okay, it's a piece of that angle measure of the circle. So if angle APB is 30 degrees, then the minor arc AB is also 30 degrees. Okay? Well, think about it. What's the degree measure of an entire circle? Hopefully you remember that as being 360. Because if the minor arc is 30, then the rest of this guy here, which is your major arc, has to make up the rest of the 360. So how do you find the major arc? You simply subtract the minor arc from 360. So, again, if angle APB is 30 degrees, then its minor arc AB is 30 degrees, and its major arc AQB is going to be 330 degrees. We just subtract 30 from 360. Okay? Oh, by the way, let's back up for a second. We talked about semicircles and diameters before, right? If I draw in a diameter and it creates a semicircle, then the measure of the semicircle, and we can call this again DE, so then the measure of arc DQE is half of that circle, or 180. Okay? So we can always use that too. All right. More vocabulary. Whew, there's a lot. Congruent arcs. Okay? Obviously, congruent arcs are going to be two arcs that have the same measure. But, and what we'll have to take a look at some other point in time, is that it has to be two arcs in the same circle or congruent circles. Okay? As a matter of fact, we don't have to worry about talking about it later. We just talk about it now, right? If I've got two circles that are not congruent, okay, and I created a central angle that had the same measure in both. Create a central angle that has the same measure in both. Let's say that both of these angles are 30 degrees. That can happen. Which means that these arc measures are the same 30 degrees. There's no way those two arcs are congruent. There's no way those two arcs are the same size. So that's why the arcs have to be in the same, or have to be in congruent circles. Okay? Even a little bit easier to see is if your circles have the same center, see, how do we do this? Okay, but still not congruent. All right? But if we create a central angle, again, this central angle is going to have the same measure for both circles, but those arcs are not going to be the same, right? So two arcs, the only way they're going to be congruent is if they're in the same circle or in congruent circles, and then they have to have the same measure. And just a reminder that two circles are congruent circles if they have the same radius. Okay, that's how we define them. All right, now, talking about arc addition here. There's something called the arc addition postulate, which means that we can add arcs together, which hopefully makes a ton of sense because we have angle addition and segment addition already, and we can kind of prove arc addition by using angle addition. But basically, if two arcs share the same endpoint, so arc AB and arc BC, if I know there's those measures and I want to find the measure of arc AC, then I'd simply add AB and BC together. Okay? Again, hopefully that makes just a ton of sense. So let's try it out. We've got an example here where we have a bunch of different arcs that we want to talk about, and we want to make sure that we understand if they're a minor arc, major arc, or a semicircle. And then we want to find the measures. Now, because we know that there's a tie between central angles, a relationship between central angles and the arc measures, what I would do is come over to this diagram first and fill in all of the angle measures. Okay? These two angles here, MON and ROQ, are vertical angles, and so they're congruent, and so they're going to have the same measure. This angle here, NOR, is a straight angle, and so now these two guys, here and here, are going to be a linear pair. They're going to be supplementary. So if I subtract 73 from 180, I get 107. Right? And then same thing here. To go from here to here, we're going to have to, it's going to be 180. So I can do 81 plus 73 and subtract from 180. So 180 minus, add these two together and you get 154. So subtract that and you get 26. So this angle inside of here is going to be 26. Now, let's go find arcs. MN, first of all, is a minor or major? Okay, minor. What about number 2, NQ? NQ is going to be minor. NQR, well, it's got 3 letters, so that's a pretty good hint, but instead of a major arc, we're going to call it a semicircle because NR are the endpoints of a diameter. MRP. M and P are not endpoints of a diameter, so this is a major arc. PN is a minor arc. MNQ is a semicircle. QR is a minor arc. MR is a minor arc. QMR. Now QMR starts here at Q, goes all the way through M, and ends at R. And so that is definitely a major arc. PQ is a minor arc. PRN, again, starts at P, goes through R, all the way to N, is a major arc. And MQN, which again, you have to be aware, you know how to follow the letters. MQN is there, and so this is a major arc. Now, minor arcs are pretty straightforward on how to find them. Right? So number 1, arc MN, it's equal to its central angle, so 73. NQ, same thing, central angle, but we're going to have to add 81 and 26 together to get 107. NQR is a semicircle, half of a circle, so that means this has to be 180. MRP, we can add this arc, and this arc together to get MRP. And so those arcs are 107, 73, and 26. Right? So that's going to be 180 plus 26, which is 206. PN is a minor arc, and it's equal to its central angle, so 81. MNQ, again, is a semicircle, half of a circle, which is 180. QR is a minor arc, and so it's going to be 73. MR is a minor arc, equal to its central angle, so 107. QMR, right? Well, there's two different ways we can do that. We can add this arc, this arc, this arc, and this arc together if we wanted to. Nothing wrong with doing that. Or, since QMR is the entire circle except for this part right here, we could just subtract 360, 73 from 360. Right? And get 297. 287, I believe, actually. Let me verify that real quick. And that's right. So QMR is going to be 287. PQ is that minor arc, which is 26. PRN, we can do the same thing, right? PRN is the entire circle except for this guy right here, PN. So we could take 360 and subtract 81 from it and get 279. And then MQN. So you can kind of piece these together however you need. MQN, again, is the entire circle except for 73. So subtract 73 from 360, and it's going to be 287 as well. Right? So a lot of these arcs are even congruent to each other because they're in the same circle. All right? Hopefully that makes enough sense. Now, a couple more examples here for you. Find the indicated arc measure. We want to find QS. QS is this guy right here. And these arcs are going to tell us these angles are the same. So if we don't know this one, which is x, then this one's going to be x also. So we can always go x plus 52 equals 360. So 2x, subtract 52, and you get 308. Divide by 2, and x is 159. So angle QPS is 159, so arc QS is also 159. This is a central angle. Okay, now we want to find LKJ. Same deal, right? These are the same, so x plus 74 has to equal 360. 2x is going to be equal to 286, and divide by 2, and x is going to be 143. Which means that this angle here is 143, which means that this arc is 143 and this one is 74. So if you add the two together, you will get LKJ, which is 217. Okay? All right, try 3 and 4. Stop the video, and then start it back up again when you're ready. Okay, a little tougher here. If this arc is 80, then this angle is 80. And then you've got vertical angles here. So this angle is 80, which means that this arc is 80. Okay? Now, if this angle, if this this angle is x, then this arc is x. Vertical angles means that this angle is x, which means this arc is x. And we can do this with the 67 as well. This central angle is 67, vertical angles makes this 67, which makes this arc 67. And if you add all the way around the circle, you're going to get 360, right? So what we need to do now is go 67 plus 80 plus 80 plus x equals 360. Okay? Big time equation there. Solve that down, and x will end up being 33. Okay? And we can kind of apply the same principle here for number 4. This arc is going to be 52 because the central angle is 52 because these guys are vertical angles. And so this arc is 52. Now this angle is going to be x to the 7th, which means this is x to the 7th. So again, if we add x to the 7th plus x to the 7th plus 52 plus 52, and that's going to have to equal 360. You have to remember how to solve using x to the 7th, which is tough. Not tough, but 2x to the 7th plus 104 equals 360. So subtract 104, divide by 2, and x to the 7th is going to be equal to 128. And then we have to take the 7th root. That's weird, isn't it? But you'll get there. Okay? And then solve from there. But at this point, don't worry about it. All right? All right. That's it. So homework's out in Canvas. Make sure you get that done by next class.